welcome to the second lecture. In the last lecture, we actually covered a few very important topics. First one was subspaces, and to recap, so we defined the subspaces uh, uh, as a subspace of R of n in any set H in Rn, which follows following three properties, right? And the first one is that zero vector is in H, and for each vector u and v, the sum u plus v is in H, and for each u in H and some scalar quantity c, the vector defined by c times u is also in H. So the fundamental property of a subspace is that it is closed under addition and multiplication. After defining that, we actually moved on to defining the basis for a subspace, and we defined the basis of subspace H that we defined earlier of Rn is a linear independently set in H that spans H, right? So it means the set of vectors v1 to vp, say for example, that are linearly independent here, for example in this scenario here in Rn, the set of all linear combinations of v1 to vp is a subspace of R of n, and of course span of v1 to vp as a subspace spanned by these vector v1 to vp. Similarly, we define the column space and null space of a matrix. And column space, this is the subspace, actually we can say, of a matrix. Is column space of a matrix is the set of is a set column of A denoted by column of A of all linear combination of the columns of A. So it means if A is a vector, which is A is a matrix that is consisting of A1 to AN columns, so all the possible linear combinations of these columns actually constitute a set which is defined as column of A, and actually the column space of that matrix. Okay. Now similarly, it is so if you need to find out that any any column vector B is in the space column space of A, what we need to do is to find the linear combinations given by the variable x such that Ax is equals to B. So we did an example in the last lecture that actually illustrate this very basic point. So which we said that if the matrix A is defined by here, and B is a column vector here, so we have to determine whether B is in the column space of A. So what we did is we used the following augmented matrix notation, and we did some row operations to determine if the solution exists, right? I mean, if the solution is consistent or inconsistent. If the solution is consistent, which we found out to be that it is, we said that B is in the column space of A, right? If the solution was inconsistent, we couldn't have said that B is in A. We have said that B is not in the column space of A. Okay. Similarly, we defined the null space of a matrix is a set null A, which actually is the set null A of all solution of the homogeneous equation Ax is equal to 0. It means for all the possible scenarios in which Ax is equal to 0, all set of vectors is defined by the set null of A. Okay. So when A has n columns, the solution Ax is equals to 0 belongs to R of n, and the null space of A is the subset of R of n. Null space actually has the same properties as of R of n, and as I defined you earlier, that it is also a subspace of R of n. So similarly, column space is also a subspace of R of n. So to test any vector v is in the null space of A, you have to just simply do is to try to find out if AV is equal to 0. It means we find the possible scenarios in which this condition exists. So if it exists, right, we say V is in null space of A. If it doesn't exist, we say it is not in the null space of A, right? Similarly, we did an example to find the basis of the null space and actually the column space, and we found we did some examples to illustrate the concept of the null space and the column space through that example and how to calculate that, and similarly the basis of how to find the basis of those column space and the null space. And the last point that we covered was so if you're trying to find the basis of column space of A, we actually have to use the pivot columns of a matrix A from a basis for the column space of A. Okay. Now, because sometimes when you are doing the row reduction, you will see here, because in the last example we demonstrated that A and B are actually the same matrices, but the thing here is B is obtained by the row reduction on A. Since we can see here after the row reduction, you can find out that B has all the last row of B is actually 0. It means if we use B to define the column space of A, we will not be able to define all the space which has non-zero values in the last row. So what we always do is use the pivot columns of A to define the basis of COL of A. It means which is the set of the set spanned by the column space of A. Okay. So in this lecture we will talk about first we'll talk about the dimension and rank. So before we define the dimension rank, let's define the coordinate system. Okay. So generally the main reason for selecting a basis for a subspace H instead of merely a spanning set is that each vector in H can be written in only one way of a linear combination of the basis vectors. So suppose if we say there is a subspace B, which is let's say B is a set of vectors B1 to BP that is a basis for H, and suppose that a vector X in H can be generated in two ways. Let's say so we can write X is equals to C1B1 plus C2B2 up to CPBP, right? And X can, so the first way you can generate the vector X, and similarly there is a second way. Let's go the first way, and the second way it's, let's say, D1B1 plus up to DP and BP, right? Now thing here is, if I subtract X minus X means 1 with 2, right? So this becomes C1 minus D1 B1 plus up to CP minus DP into BP, right? Because X are the same vector, this is actually 0, right? So in effect, so remember this, since B1 to BP are linearly set of independent vectors, it means, if you remember from our discussion from the linear independent vectors, they only have the trivial solution. So it means C1 minus D1 is equals to 0, C2 minus D2 is equals to 0, and similarly CP minus DP is equals to 0. It means C1 and D1 are same, C2 and D2 are same, CP and DP are same. So it means any vector X in the subspace can only be written in one way. So it means either since C1 and D1 are same, it means X vector can only be written in one form. It means it can be written either as, actually can be written as C1, okay, and because C1 is equal to D1, so nothing will change. So only this vector X can be written as in in one way. So there are no two representation of vector x. There are no different linear combinations of these basis vectors that can generate x. There is only one combination, one linear combination of the vector, this basis vector, that can generate x. Okay. Now suppose that the set B, which is the set containing the basis vector for the subspace, right? Then for each h in x, right? Oh, sorry, for each x in h, the coordinates of x relative to the basis B are the weights C1 to Cp such that x is equals to C1 B1 plus Cp Bp and the vector in Rp, right? So we define the coordinate system for that basis as something like this, right? So C1 to Cp, okay, and it is called the coordinate vector of x relative to B, of course, or you can say, or the B they can be italic B coordinate vector of x. Okay, so let's do an example to illustrate what we have just said about the coordinate system of the subspace. Okay, now let's say we have the vector v1 and v2 and there is a vector x 3, 12 and 7. Now B is a subspace, the set of subspace containing v1 and v2, of course. Then v1 and v2 are actually linearly independent. Now, so we know that if these are the linearly independent set, then the subspace H will be spanned by v1 and v2. Now we have to determine if x is in H first of all, and find the coordinate vector of x relative to B. Okay, now to do that, right, so we have to find the values of C1 and C2, right, for the first part, that determine if x is in H. So it means if C1 and C2 exist, right, then x vector will be in the span of v1 and v2. Okay, now if C1 and C2 doesn't exist, right, or the solution is inconsistent, it means x will not be in the subspace spanned by v1 and v2. Okay, so to do that, right, we know from our previous discussions we can write this as an augmented matrix form, which is 3, 6, 2, minus 1, 0, 1, 3, 12 and 7. So what you do is multiply the first row with 2, subtract it from the second row. Okay, and then you can do the simply swap the first and the third row, and then do some multiplication on the third row. So you will get this form, which is 1, 0, 0, 0, 1, 0 and 2, 3, 0. So you can see here this is 3 columns here, right? Now from our discussion previously, we can find out that C1 is equals to 2, right, and C2 is equals to 3, right? So it means the value of C1 and C2 exist, and of course, as we discussed earlier, these are unique values. if a vector x is in subspace, in the subspace spanned by v1 and v2, right, it can only be written in one form, not in two different forms. So there will be unique values of c1 and c2. So there are no other possible values of c1 and c2 for which you can write for this to be true. Now the second is we have to find the coordinate vector of x relative to b. So the coordinate vector of x relative to b is nothing but x of b is these coefficients, which is c1 and c2, which is equals to 2 and 3. Okay, now since the bases determine the coordinate system, now you can actually think of, now if I want to draw it, you can actually think of this as not exactly the same thing, but you can virtually think of this one as v1 and v2, right, and this is your c1 and this is your c2, right, and so this will be your vector x, right. Remember this is in 2 dimensions, okay, right, these are 2 dimensions. If you see here, the actual vector x is in 3 dimensions, okay, but when you define the subspace, right, this vector actually x, if you convert it from a normal 3-dimensional space, right, to the subspace defined by these vectors, right, you can write this vector as a combination of 2 vectors, but it will be in 2 dimension, not in 3 dimension. Okay, so here the dimension, so from that discussion, the dimension of the subspace is actually 2. So dimension of this subspace is 2, okay, because v1 and v2 are only 2 vectors. In a 3-dimension case, right, for example here in Rn, so let's say R cube, we have 3 vectors. This is v1, could be v1, or let's say v2, this is v3, okay, but the subspace has only 2 dimensions, okay. So then if you can notice here again, although the point in H are also in R cube, so the space, the points are in H cube, right, in H, which is in R cube, right, they are completely determined by their coordinate vectors v1 and v2, which belongs to R square. So which belongs to R square, that means x b is equals to 2 and 3. So these are the coordinate vectors that completely defined x in the relative to the vectors in B, okay. Now the correspondence, which is x is 1-to-1 correspondence, because remember I told you earlier, there are only unique value of c1, c2 and c1 and c2 that determines x, right, and we have proved it earlier as well that if the basis set of basis vectors b1 to bb, and we say any vector x is in that is spanned by that basis, that can only be written in a single unique form, right, they cannot be written as a linear combination, 2 different linear combination of the basis vectors. So x of b is 1-to-1 correspondence between H and R square that preserves linear combination. Now this correspondence is called isomorphism. And we say that H is isomorphic to R square. Okay. So you can see the grid in figure 1. Make you look like that H actually look like R square, but in fact that relationship from H to R square is preserved through linear combinations that are defined by this coordinate system relative to B. Okay. Now so now we can actually define, based on this discussion, we can define the dimension of a subspace. Okay, so if a subspace H has a basis of p vectors, then every basis of H must consist of exactly p vectors. So this is the fundamental to defining the basis and dimension of a subspace. In effect, the dimension of a non-zero space denoted by dimension of H is the number of vectors in any basis of H. So the dimension is actually the number of bases vectors in H, right? So the dimension of a zero space of a zero subspace is often denoted by 0 is defined to be 0. So again, we repeat that again. The dimension of a non-zero subspace H, denoted by this term here, is the number of vector in any basis of H. So in the previous example, there are only two vectors that are defining the basis of H. It means the dimension of that subspace was 2. Okay. So if you want to generalize here, so the space R of n has dimension n, right? And every basis of R of n, so every basis of R of n consists of n vectors, right? So in this case, a plane through 0 is R square, a plane through 0 is 0 in R square is two-dimensional, and a line through 0 is one dimension, and a line through 0 is one dimensional, right? And you remember from the last lecture that subspace, the property of the subspace, that 0 vector should be in the subspace, so everything has to pass through 0 for a subspace. Okay, now let's relate to what we have just discussed to an example that we did previously. If you remember that when we were discussing the null space of A, and we were told, we've been asked to find the basis of the null space of the matrix. So the dimension in this case, if you remember this was this matrix A, and what we did was, since null space is defined by solving Ax is equals to 0, and when we did that, remember, we end up actually with this matrix by using row reduction, and we found out that you can write this in the form x1 minus 2x2 minus x4 plus 3x5 equals to 0, and x3 plus 2x4 minus 2x5 equals to 0. And when we wrote it in the form like this, it came out to us that there were 3 vectors that were defining the null space of this matrix A. Okay, now so we can see here the dimension of this null space from the definition that we just did in our previous slide here. So the dimension of a zero space, dimension of a non-zero subspace as denoted by image, is the number of vectors in any basis of H. So from the discussion we can see here that we have 3 vectors for that basis of the null space A. So the dimension of this null space is actually 3, and you can see here, as we have discussed earlier as well, the number of free variables actually determine the basis vector. That if there are 3 free variables, it means we have got 3 basis vectors. If there are 2 free variables, we got 2 basis vectors. So number of free variables actually determine that how many basis vector you're going to have in a column space, or sorry, in a null space of the matrix, not the column space, sorry about that. In a null space of A, number of free variables will determine that how many basis vectors that we will have for the null space of a matrix. Okay, now so similarly we can define, once we have defined the dimension, we can define the rank of a matrix. So the rank of a matrix is the rank of matrix A. So rank of a matrix A is denoted by rank A is the dimension of the column space of A. Okay, so for example, if you want to determine the rank of the following matrix, which is 2 4 6 0 5 7 9 minus 9 minus 3 minus 4 minus 5 6 minus 4 minus 3 2 and 5 8 9 4 and minus 6, right? So what you have to do is to reduce this A to an echelon form, and when we did that, right, so you take the first row multiplied by 2 and add it here. It's subtracted from the second row. Okay, similarly what you can do is again multiply this by 3 and subtract it from the third row, and once you have the pivot for that column, right, again you try and finding the pivot for the second column and the third column and the fourth column, and so on and so forth, right? So it means if I do a lot of operations here, I end up in a form like that, and you can do it your home as well. So I'm take these small steps as your assignments, and you 5 minus 3 0 0, and you got here minus 3 2 0 0 and minus 4 5 4 and 0, and then you have 8 minus 7 minus 6 and 0. right? So we can see here there are this is a pivot column, and this is a pivot column, and this is a pivot column, right? So there are 3 pivot columns here, right? And uh, of course, right, so the matrix has 3 pivot columns. So the rank of A is equals to 3, and if you remember from the last lecture, that's what we advised here, right, that the pivot columns of the matrix A form a basis for the column space of A. Okay, and this was the column space, right? And column space of a matrix is a set of column of A of all linear combinations of the column of A. So this is the column of A is the same as span A1 to A2, right? So this was the discussion that we carried out last time. Okay, now so the matrix has 3 pivot columns and rank of this is 3. So for example, now the row reduction here in this example illustrates that there are 2 free variables. Okay, so we can see from here as well that there are three free variables, because 2 free variables. So because this is 1 2 3 4 5, and we have 1 0 here, so you can see here we got 2 free variables and there are 3 pivot columns. So it means the remaining 2 columns will actually relate to the free variables. So it means since the number of pivot columns plus the number of non-pivot columns is exactly the number of columns, so pivot columns plus the non-pivot columns should be equals to 5 in this case. So this is non-pivot columns 5 minus 3, which is equals to 2. So these are 2 is the number of free variables. And if you remember, just 5 minutes ago we discussed that these non-pivot columns relate to free variables, and the number of free variables determine the null space, dimension of the null space of any matrix. So what we can write here is that rank of A plus dimension of null of A should be equals to n, because rank of A is the dimension of the column space of A, and actually you can write it as dimension column of A plus dimension null of A should be equals to the number of columns. Okay, so hopefully now you have understand why do we need to study the column space and the null space, that you can broke down the number of columns into the dimension of the column space and the null space. So this leads to what we call is the basis theorem, right? So let H be a p-dimensional subspace of Rn. Any linearly independent set of exactly p elements in H is automatically a basis for H. Also, any set of P elements of H that spans H is automatically a basis for H. So what we are saying here is, to do an example, so if there are a set of P, let's say P vectors, right, and they are linearly independent, okay, so if H is a P-dimensional subspace, right, and there are this linear independent vectors in that subspace, right, they can completely serve as the basis of that serve as the basis for that subspace. And say, let's say, assume there are another set of vectors d1 to dp, and they are linear independent, and also they are in the subspace of H, right, they can also serve as the basis. So that's what it says. Let H be a p-dimensional subspace of R of n. Any linear independent set of exactly p elements in H is automatically a basis for H. Also, any set of p elements of H that spans H is automatically a basis for H. So that's what he said. Any two different sets which are linearly independent and can actually span H becomes a basis for H. Okay. So now this leads to what we know as the rank and the invertibility theorem. Invertible theorem. Okay. So if I say let A be an n by n matrix, so the following set of statements are actually equivalent to the statement that A is an invertible matrix. Okay, so if any of the condition is true, it means A is an invertible matrix. The first one is the columns of A form a basis of R of n. So it means the columns of A, it means A matrix, the columns A1 up to AN form the basis of R of n. So it means in which dimension they are existing. So it means in n dimension they form its basis, right? So they're actually, what we're saying here, they are actually linearly independent. A1 to AN are actually linearly independent set. Okay. Okay. Now the second one is column of A is exists in R of n. So the set spanned by the columns of A, okay, is actually in n dimension, right? And third one is dimension of column of A is equals to n. So the dimension of the set containing all the possible linear combinations of A1 to AN has a dimension of n. Okay. And the fourth one is the rank of A is equals to n, and the fifth one is that the null of A is a vector space defined by the subspace defined by Ax is equal to 0 is actually 0. Okay, and the sixth one is the dimension of, in effect 5 and 6 are the same, null of A is equals to 0. Okay. Now let's do some examples based on what we have studied today. And now let's say we've been asked to determine the dimension of the subspace H of R cube spanned by the vectors v1, 2 minus 8 and 6, v2 is equals to 3 minus 7 and minus 1, and v3 is equals to -1, 6, and -7. Okay, now so we have to determine the dimension of the subspace H of R cube. So it means it is quite actually easy. So what we do here is build a matrix A, V1, V2, and V3, and when you put it here, that becomes 2, -8, 6, 3, -7, -1, -1, 6, and -7. And if I do the row reduction on that one, so that becomes 2, 3, -1, 0, 5, and 2, 0, -10, and -4. And if I do it further again, that becomes 2, 3, -1, 0, 5, and 2, 0, 0, and 0. Okay, now see here, the first two columns, this one is a pivot column, this one is a pivot column, this is not a pivot column. So since the first two columns of A are pivot columns, right, they form the basis of H, right? So they form the basis of H, right? Because thing here is, you can see that there is a free variable here, okay, and we know that whenever there is a free variable, null space is not 0. Okay, so null space have a dimension of 1. Okay, okay, so it means we can say the dimension of that H spanned by the vector v1, v2, and v3 is actually 2. Okay, now let's do the second example. Now consider the basis which is defined by b is equals to 1.2 and 0.21, right? So it means this basis got two vectors, which is this is v1, this is v2, or you can say this is b1, this is v2, keeping with the keeping in line with the previous notations for r square. Okay, so now if x of b is equals to 3, 2, what is x, right? Because you know this this has a one-to-one correspondence when we're doing with this coordinate system, so dealing with this coordinate system, so you can find x of b to x is equal to nothing but 3 times this vector b1, which is 1.2 plus 2 times 0.21, which is equal to nothing but equal to 3b1 plus 2b2, and when you add them up, you get here is 3.4 and 2.6. Okay, again, now let's, so can you, so could r cube possibly, this is the third example, could r cube possibly contain a 4-dimensional subspace? Now I'll just give you a minute to think about it before I'm going to write the answer. What do you think, could R cube possibly contain a 4-dimensional subspace? Actually, it is not possible to fit in a 4-dimensional subspace in R cube, because remember a 4-dimensional subspace will require, actually will require 4 linearly independent vectors. Right, and actually in a three-dimensional space it is not possible to define four linearly independent vectors. Okay, if you do that, right, you will find out, try to fit in, if you try to fit in that, you will find out any of the four vectors will be written as a linear combination of the other three vectors, right? So the space R cube itself is only a three-dimensional subspace of R cube. So the space R cube itself is the only three-dimensional subspace of R cube. So only dimensions, subspace dimensions that you have in R cube can be 2, 1 or 0, because if you're trying to define the subspace of R cube, you can only define itself as a subspace. So you can actually say that the number of subspaces that you can define in R cube is 1, right? But if you want to define a subspace, a dimension 2 subspace in R cube, then you can do that. Dimension 1 subspace in R cube, you can do that. And dimension 0 subspace in R cube, there could be many. I mean, in this case it could be, I think, 3, 2, I think that will be 3. In this case you will have I think that will be, again, we'll have 1, 2, 3, we'll have 3, and then you can have is infinite if you want to define that. Okay, now this brings to the end of this lecture, and let's revise what we have just covered in this lecture, and please let me know if you have any difficulty understanding any of the content that I'm discussing on these on the slides. Okay, now so initially we talked about the dimension and the rank. To understand the dimension and the rank, we have to really first understand the coordinate system, and the coordinate system that is defined in the subspace. So we say the vector b, which is the linear set of independent vectors that define the basis for the subspace H. So suppose that an x is in H can be generated in two ways. It is not possible. Okay, so in the coordinate system, a vector x can be generated by only one and one method. For example, in the case of a two-dimension space, say for example, let's say this is x and this is y, right? If this is a vector r, there is only one unique way to determine r by the values of x and y. There are no different values of x and y that can generate this vector vector r. Okay, so similarly in the case of subspaces, again, there are, so if you are defining a subspace by the set of basis vectors, so there is only one possible set of linear combinations that can define x. There are no two different linear set of linear combination of these basis vectors that can generate x. Okay, now similarly, as we define the coordinate system of r of n, similarly we are defining the coordinate system for the subspace, and the coordinate system of subspace is actually the coordinates. So b1 become one coordinate, b2 become another coordinate, b3 become another coordinate, b4 becomes another coordinate, and similarly bp will become another coordinate, right? So so coordinate of x relative to the basis b are the weights c1, cp. Similarly here, for example, if this is 1, this is 1 here, we normally write 1 and 1. So these are the weights of x and this is the weight of y. Similarly, c1 and c2 are are the weights of the vector, okay, that needed to be put in place to get x. Okay, so x, the x that you can define in the vector space in the or relative to the basis vector set B is the coefficients of those linear combinations. So C1, C2 up to CP. Okay, so this is called actually the coordinate vector of x relative to B, or the coordinate vector B coordinate vector of x. Okay, so we did an example to illustrate how how these are related. So these, for example, let's say we define v1 and v2, and we can see v1 and v2 are independent, so they can actually define a subspace, right? And and we were asked to determine if this x vector, this column vector x, is spanned by v1 and v2, right? So if b are the basis vectors v1 and v2, to determine if x is in H, right? So it means there's some sort of linear combination C1 C2 that exists that can that should be equals to x, right? And we know that this is equivalent to finding, it's very similar to the system of linear, so the solution of system linear equations, which we can build by using an augmented matrix. So we did an augmented matrix, we built an augmented matrix, and we turned to find the solution of that. And when we converted into a reduced echelon form, we found that there exist two possible solutions, which there exists the value of C1 and C2 for which C1 times V1 plus C2 times V2 is equals to x. So it means x is in H. So we can easily say that x is in H, and what you have to do is to find the coordinate vector of x relative to B. So coordinate vector of x relative to B is the values of the coefficients that have been scaling the vector v1 and v2, which is in this case is c1 and c2. So the so x relative to B is c1 and c2, which is equal to 2, 3, and I demonstrated here that this can be thought of v1, this can be thought of v2, and you can, this is the weight c1 and c2. So here this is c1 and c2, which is very equivalent to how we deal with Euclidean spaces. Okay. Now we also define that x and xp is one-to-one correspondence, because the way that we have defined it, right, since there is only one unique way in which the linear set of combinations can lead to x, so it means x to xp is actually a one-to-one correspondence. So you can go from here to here or here to here. So as I demonstrated in the last example that we just did, so in how you can actually go from here to here. In this example here, we showed you how you can go from here to here. Okay, so this example demonstrates how you can move from here to here, and the example at the end of this lecture that we just covered told us the method how you can move from here to here. Okay. Similarly, we defined the dimension of a subspace, and we said that the subspace is the basis of p vectors, then every basis of H must consist of exactly p vectors. And the dimension of, before we defining the dimension, we defined that, and the dimension of a non-zero subspace H, denoted by dimension of H, is the number of vectors in any basis of H. So number of vectors in any basis of a subspace actually is the dimension of the subspace. Okay. So I related with the example that we did in the last lecture, that the dimension of that null space was 3. Okay. Similarly, we moved on to define the rank of the matrix, and is actually rank of the matrix is the dimension of the column space of A. So it means if A has we have to determine the column space of A, we actually have to determine the number of linearly independent vectors in A. Okay, so so once we did that, or alternatively we can actually say that either you would find the linearly independent vectors, the number of linearly independent vectors in A, or either what you do is to find the pivot columns in A. So when we did some kind of reduction, we found out that the number of the matrix has 3 pivot columns, and in this case the rank of A is 3. So we know that the pivot columns plus non-pivot columns is equals to 5. The number of non-pivot columns in this case is equals to 2. And I also related with the example in the previous lecture that actually number of free variables, because number of non-pivot columns actually tells you the number of free variables in the defined by the matrix A. So it means the number of free variables also define the number of basis vectors for a null space A. Okay, and in this case rank of A plus dimension of null of A is equals to n. So number of free variables equals to number of basis vectors of null space, and which is also a dimension of null space of A. Okay. Similarly, we covered the basis theorem, and once we did that, we looked at some of the properties of rank and the invertible matrix with the discussion that we just had, and we did some examples to illustrate one of the key concepts that we covered in this lecture. I hope that you are grasping the content of what has been discussed in these lectures. But if you have any questions, please leave a comment on the YouTube link, or I mean, it will be much better if you can actually put it on the Canvas portal. I have opened a discussion about the lecture, so please use that space to point out if you are having any trouble in understanding the content, and please leave and let me know how you guys are doing and how things are progressing with you. Thank you.